This is fundamental problem 11 from chapter 12. It is our first problem from section 12.3. You don't feel like this section needs an introduction. You should read through it on your own, but basically all they're telling you in section 12.3 is when you take the derivative, that's the same as looking at the slope of the graph. When you do the integral, that's the same as looking at the area underneath the curve. So we should be familiar with that from Physics 161. Fundamental problem 9 and fundamental problem 10 are homework problems. In these two problems, you have position versus time and velocity versus time. Fundamental problem 13 is a homework problem, and for this one you have acceleration versus time. So for all three of these graphs, you have time on the x-axis, and you should have seen that many times in Physics 161. What we didn't see often, if at all, in Physics 161 was graphs of velocity versus position or acceleration versus position. You may have seen graphs like that in lab, but I don't think we did anything with those graphs in lecture. So we're going to look at fundamental problem 11 with a velocity versus position graph, so this might be new for you, which is why we're doing this problem together. So in fundamental problem 11, we have a bicycle traveling along a straight road where its velocity is described by the velocity versus position graph, which is given below. We want to construct the acceleration versus position graph for the same time interval. Okay, now when we have a function of position, usually we're going to be using equation 12.3. However, we did see that if we want to use equation 12.1 and equation 12.2 instead, we can always do that instead of using equation 12.3, since equation 12.3 can be derived from equation 12.1 and equation 12.2. But we are going to use equation 12.3 here, and we want an acceleration versus position graph. So first of all, I'm going to draw the graph that they give me in the problem, which is velocity versus position. It's linear, and the slope is 0.25, and we have at 40 meters, we are at 10 meters per second. I don't know what happens after 40 meters, so that shouldn't be there. Okay, and we want to construct the acceleration versus position graph. Okay, so I know that A ds is equal to V dV. Now what am I going to do with that? I need the acceleration as a function of position. I'm going to bring the ds over to the other side. So I have A is equal to V times dV over ds. And we saw in a previous problem how this equation can be derived from 12.1 and 12.2. So if you don't like just bringing the ds over to the other side like that, you can see that this is actually true by looking at equation 12.1 and equation 12.2. Okay, so I have position there. I have velocity as a function of position. And so this dV ds, this is the slope of my position, or my velocity versus position graph. Well, the slope of my velocity versus position graph is 0.25. This is a 0.25s. I don't know if you can see that. So let's write that again. Velocity is 0.25 times s. So dV ds is just equal to 0.25. So now I'm taking my equation for acceleration. I have acceleration is equal to velocity times 0.25. But this isn't a function of position, it's a function of velocity. So all I need to do then is take this and put that in for the velocity, and then I have the acceleration is equal to 0.25 times s times 0.25. And so finally we have acceleration is equal to 0.0625 s. Did it ask me to graph it? Construct the graph for the same time interval. Okay, well that's pretty easy because this is another linear graph. Here we have acceleration and position. If velocity was in meters per second and position was in meters, then acceleration would be in meters per second squared. When s is equal to 0, the acceleration is equal to 0, so we have something linear here, and the slope is 0.0625. Well, we could say since this graph here ended at 40, we can say this one here ends at 40. And if you really wanted to, you could figure out the corresponding acceleration when the position is equal to 40. I forgot the S there. But we don't need to do that. Okay, so here's our graph. And what we should notice about this is, unlike when you have velocity as a function of time, if velocity versus time was linear, acceleration versus time is flat. But here, velocity versus position is linear, and acceleration versus position is also linear because it's the velocity times the slope of the velocity versus position graph, which is equal to the acceleration. Okay, so that concludes fundamental problem 11.